almost noon, folks. Thank you for tuning in for another one of our cosmic conversations. My name is Josh Roberts. I'm one of the planetarium staff at the Morrison Planetarium, California Academy of Sciences, and we are here today with someone I am very excited to introduce to you. This is Dr. Pascal Lee. Dr. Lee is a planetary scientist at SETI, a director of the Mars Institute, and is a scientist at NASA Ames, just down the road from us in San Francisco. Dr. Lee, how are you today? Oh, we have you muted. Sorry about that. You're back now. How are you today?
Yeah.
Wonderful.
Sorry. Good. How are you doing?
Very well. We've got a beautiful view of planet Earth. We've got a really cool program, and we're going to hear all about human exploration out beyond the surface of our own world. So, Mary is our producer today. Can you take us over to our view of Earth in open space? So we've got a really awesome view. We can see the dark side of our planet where human beings are living, silhouetted against that beautiful star-filled sky. And we are talking today about some of the ideas about humans leaving planet Earth and taking off to see some of these other places. Pascal, can you tell us about some of the ideas about where human beings might end up next?
So we've been to the moon, but we haven't been back to the moon with humans for over 50 years now. And so, well, close to 50 years, because the last human landing was in 1972. Before we launch ourselves onto Mars and to these other greater places at greater distances, we need to go back to the moon. The moon, first of all, still has plenty to be discovered about. And then the other thing is, it's in the immediate neighborhood of the Earth, and so it's a good place to practice, to get ready for more ambitious exploration activities like what we have in mind for Mars. Now, right now, NASA and hopefully a growing number of international partners are planning to go back to the moon within the next few years and land the first woman and the next man on the moon near the south pole of the moon. And the reason why the polar regions of the moon are interesting is because there is water ice there. And of all the things that are of interest on the moon, water ice is super interesting because, well, not only is it a sort of a key ingredient for us humans and life on Earth, not that we expect any life on the moon, but it's a key ingredient for life in general. It's also something that we can use as rocket fuel by breaking down the H2O into hydrogen and oxygen. And it's also something that can tell us a lot about the origin of the moon and how hot it was when the moon formed. And right now, the current general idea is that the moon formed as a result of the impact of an object that was about the size of the planet Mars, although there are some variants to this hypothesis, that would have hit the proto-Earth. This is when the Earth was slightly smaller than it is today. And some of this material from this impactor, the size of Mars, got incorporated into the Earth. And so the Earth grew to its current size. And then part of the debris that swung around the Earth and got turned into a ring of debris eventually accreted into our moon. And so the moon basically has a very fiery origin in this whole scenario, and there are questions about how hot this disk of gas was and how much water the moon could have retained from the original body that slammed into the proto-Earth. So the fact that we're finding ice in the polar regions of the moon is really intriguing. Is this ice sort of strictly a late addition to the moon from comets that hit anywhere on the moon, but then the water molecules from the comets get liberated during the impact and migrate over time to the coldest spots where they condense and basically stop migrating? Well, that's a process called cold trapping. So we think that one scenario is that the lunar polar regions are so cold because there are some places there that never see the light of day. They never see the disk of the sun. They're in perpetual darkness. The lunar poles are so cold that you're a little molecule of water bouncing around on the moon wherever you were released by, say, a comet impacting the moon. You would eventually make your way to one of these cold traps. And then once you hit one of these cold traps, well, then now you're trapped because it's so cold. You can remain as you sort of keep building up the ice deposit there, and that's how we think part of the ice in the polar regions of the moon sort of came to be concentrated there. But there are other processes. There's solar wind hitting the regolith, forming and releasing some water molecules that have sort of a similar fate. There are also other ideas about how the lunar rocks in the first place, from the very origin of the moon, might still have retained some water. And we actually know this for a fact now because we've been reanalyzing some of the Apollo samples. I say we, not me, but scientists who are experts at that, reanalyzing Apollo samples and found what you might describe as juvenile water in these rocks. In other words, water that dates back to the origin of these rocks that were all this time trapped inside the moon and now can be sort of extracted from these samples that the Apollo astronauts brought back.
It's strange to think of water that old being referred to as juvenile water, but I guess that's it hasn't been used as much as the rest of the water.
Yeah, it's juvenile from the standpoint. That's a good point. It's juvenile from the standpoint of when it got sort of incorporated into the moon. But there you have it. So the lunar polar regions are a strategic location for that reason, and this is why we're so focused on trying to get humans not only back to the moon, but back to the polar regions, where you have these once again permanently shadowed regions, PSRs. If you are at a cocktail reception with some lunar scientists and you want to come across as knowing what you're talking about, you would never say, okay, it's permanently shadowed region. You'd call them PSRs. Okay, so
which is different than the PSLs we've been hearing about.
Okay, so how's your mission to the PSR going? Okay, that's planetary scientist talk. Anyway, what I want to talk to you about today, and in fact, I'll be referring to some work that I've been doing with some students as well today, but what I want to talk to you today is sort of an alternate location where we think we might be able to find ice on the moon. And this is really intriguing. So you've homed in here on an interesting large impact crater called Philolaus crater. It's at 72 degrees north on the moon on the Earth-facing side. So when you look at the moon, you can actually see Philolaus.
We can back up to give folks a little bit of perspective.
If you were
it's got those distinctive two humps right in the middle, which makes it kind of easy to pick out.
Yeah. For a large crater, for a crater this size, it's about 70 kilometers across. It's actually a relatively recent crater on the moon. It's from the latest geologic era on the moon called the Copernican era, if you care to know. But the point here is that it's a relatively well-preserved, fresh, large crater. And you can see that there's a flat area on the floor of Philolaus. Yeah, right there. And that's an impact melt sheet. The impact that took place, whether it was an asteroid or comet, we don't know, but the impact that took place was so energetic that it literally melted some of the target rocks and the impactor itself. Probably the impactor itself actually was most likely entirely vaporized in this scenario, but the impact melt sheet essentially is made of originally of molten target rocks, and it sort of pooled in the bottom of the crater. And eventually, once it cooled off, turned into this very relatively smooth surface. Well, what's interesting is that this cooling off process was not very sort of sudden. And while some parts were cooling off, other parts were still molten and flowing around, oozing around. And so we ended up having essentially impact melt lava flows crisscrossing this impact melt sheet. And if I can request some of the pictures that I brought along with you, because I'm going to show you what is really intriguing here that we're finding in these impact melts. Okay, so on the left you see Philolaus crater. We're going to zoom in onto the flat area, the impact melt sheet. As you come in closer, each photo is sort of nested from the previous one. You come in closer, you start seeing some of these collapsed lava tubes. Those little gouges that you see crisscrossing the lunar floor there are technically known as sinuous rails. In other words, they are essentially depressions that are meandering along the lunar surface. And these meandering little valleys are not really valleys. They are what we think there were once lava tubes. In other words, lava flows that were underground, with the top surface being cool enough to be rigid, but the lava still being hot and molten and flowing underneath. And eventually, when the lava flowing stopped, the overlying crust would collapse, and now you end up with this valley-shaped meandering depression called the Sinuous Rails. So Sinuous Rails are essentially collapsed lava tubes. Now, if we zoom in closer, let's go to the next slide, you start seeing that some of these sinuous features are not collapsed entirely. They are in some places marked by actually dotted lines, so to speak. Okay, so this dotting is really interesting because what we think these are partially collapsed lava tubes. And therefore, you might still have a tunnel or a cave underneath there, where in those sections that are not entirely collapsed yet. Let's zoom in further. And then some of these darker spots we think are skylights. In other words, collapsed little portions of the roof of lava tubes. In other words, cave entrances to underground caves on the moon. And of course, pits and caves have been found on the moon now for over a decade. We actually know of over 300 pits and caves on the moon. But most of the ones that have been found, and this is largely the work of Mark Robinson and Robert Wagner, but also from the Kaguya team in Japan, most of these pits and caves that have been reported so far are at low latitudes. And these caves that are at low latitudes are going to be too hot, we think, to cold trap any water ice, because sunlight will sort of shine down into the pit and will warm up the rocks at the bottom of the pit, and the rocks will radiate their heat into the cave. And so you end up at low latitudes with caves that are still interesting to explore, but that are not going to be cold. What's interesting here at Philolaus is that if these little things that are pointing out here are confirmed to be skylights or cave entrances, then you are dealing with caves in which sunlight never enters. The sunlight is so grazing near the North Pole of the moon here where we are. We are only 500 kilometers from the North Pole of the moon. The sunlight is so grazing year-round that it never hits the bottom of the pit, and therefore the rocks at the bottom of this pit never get heated. Therefore, these caves are super cold. In fact, they are as cold as the PSRs in the lunar polar regions. And so now, all of a sudden, we have a sort of a different setting in which we might be able to find water ice cold trapped on the moon. Of course, we don't know this. This is pure conjecture. But it's really
exciting
intriguing.
Possibility, though, for sure.
It's an exciting possibility, because now you're talking about finding ice in an environment that would be sheltered from radiation and micrometeoric bombardment. And, Philolaus crater is approximately, it's less than 1 billion years old or so. Copernican age terrain on the moon are 1.1 billion years old or less. So it doesn't take us back to the origin of the moon, but it could still be very ancient water if there's any trapped inside these lava tubes. And the water could be coming from outside, but it could also be water from the final cooling of this impact melt sheet. If some water was mobilized by the molten rocks. Anyway, the bottom line is this: there are caves all over the moon, but my favorites are these intriguing candidate caves near the North Pole of the moon. I reported these about 2 years ago now, but this summer with a new student, Winnie Avent II. With Winnie, we mapped out more of these candidate pits inside Philolaus, and we found some new ones in a nearby crater called Anaxagoras. But before we go there, let me show you the next few slides real quick. There you go. This is some of the best images that we have of the pits inside Philolaus.
Oh, wow.
So sunlight is coming from, don't be tricked by the lighting, okay? Sunlight is coming from the bottom of the image here, okay? And what's really intriguing is the brightening that you see right on the top part of each pit, okay? Because That's indicative of a funnel, but also of the possible vertical wall that is slightly lit by the sunlight, but not all the way into the cave. Okay, so we're very intrigued by this. And there are tens of them, at the very least, that we have, that we think are reasonable candidates inside Philolaus's impact melt sheet. Next slide is showing you sort of what this might look like in section. Okay, so the light grays there is the impact melt sheet surface at the top on the surface of the moon. Sunlight is coming in at an angle. You can see the sunlight can hit part of the vertical wall of the pit, of the skylight pit, but does not hit the floor of the cave. You have a lava tube underneath, and right underneath the pit, the environment is such that temperatures could be as cold as in the PSRs in the polar regions, and you might actually have a deposit of ice. So we did a bit of math on this, some back of the envelope modeling, and if you have a layer of, say, 1 meter of water ice accumulated there at the bottom of this 30-meter pit, or 15-meter pit actually in this case, you would end up with something like 7 metric tons of water ice.
That's
ready
substantial.
for you to, that will fill several lunar landers.
Now, we noticed you had that little portrayal of human beings down there, and I've heard these things put forward as like science fiction ideas of where human beings might live. I feel like you'd have a hard time convincing people to go live in a lava tube that hasn't collapsed yet. Like, that sounds like a pretty scary environment just because rock would fall on you.
That's a good point, Josh. I'm attracted to lava tubes, but to explore them, not to live in them. Lava tubes on the Earth are not like your regular caves. I mean, human beings have used caves for a long, long time to, as shelters, but most of them are in karst. In other words, in limestone and dolomite, not in lava tubes have been much more rarely used as dwellings, especially for any long-term dwelling. Of course, there's plenty of short-term dwelling uses of lava tubes, but not for the long term, because they're very harsh environments. And on the Earth, it turns out they are always very far from liquid water as well, unlike limestone caves, which almost by definition are near liquid water. So anyway, caves are prone to collapse. Yeah, they can be
scary.
And this is Anaxagoras, right?
Mm-hmm.
Yeah, so this is the other Copernican age large crater, Anaxagoras, not too far from Philolaus, and actually close to the central meridian.
You can see Philolaus right
Earth.
there.
Yeah, exactly. And Anaxagoras has some candidate pits as well, found by student Winnie Avent II, and I'm very proud of that work. It's exciting. So who knows? We might want to send some robotic precursors into these regions first to make sure there are pits to begin with and caves, but then humans could eventually follow. Nobody's advocating that humans go into caves up front, but it's something to bear in mind because water is everything on the moon, and almost. And as much effort as we're putting into going to the permanently shadowed regions of the poles, we should also not forget that there are also caves that could harbor water ice.
Well, it sounds like we are exciting environments not just on our moon, but we wanted to take folks a little farther out. Can you tell us about our next destination?
Next stop, Mars. So Mars, of course, is what I dream about, and where many people, of course, want to go and send humans. Mars is so exciting, so interesting. Incidentally, as much as I wasn't so hot on settling lava tubes on the moon, I'm not big on colonizing Mars either. However, I'm very big on exploring Mars. I want humans to go there to check out the place, really, and to explore it in depth. Colonizing is, first of all, it's going to be somebody else's problem, but to me, it's less attractive as a proposition as much as sort of moving on to the next place after that to explore. But Mars has plenty to explore, and so let's talk about this. Something historic happened just a few years ago. In 2015, NASA, and in particular, NASA convened the first international conference on human landing sites and exploration zones on Mars. This is really historic because for the first time, NASA sort of brought together the community of scientists and engineers who were potentially interested in proposing landing sites for humans to start planning where we might go to on Mars if when the time comes. And it's a big step. Imagine it happened for Apollo when we decided to go to the moon. All of a sudden, we had workshops and teams of people coming together to propose landing sites for astronauts. When you start thinking of a landing site for humans on Mars, that's when things are getting serious. Mm-hmm. So things started getting serious in 2015, and maybe I can show some of the slides that I've set aside for this.
Certainly.
Yep. So here's the map compiled by NASA of the 47 or so, I think 47 or so landing sites and / exploration zones. So a landing site is sort of a spot that's a few kilometers across where you would actually land all your assets. And then the exploration zone is the 100-kilometer circle, so to speak, that goes around each landing site. Okay, so we were to propose these landing sites, and here they are. Here they are mapped out. So they're all over the place, all over the map. And the one I'm going to talk to you about, the one that I'm strongly biased in favor of, is the one that is near the triplet of volcanoes in the Western Hemisphere there, on the left side of the map, called Noctis Landing. Okay, but let's go to the next slide. So this is actually showing you the constraints we were put under to propose these landing sites. First of all, they could not be too far north or too far south. That's why the high latitudes are shaded, because at those latitudes, it's essentially too cold. And there's also not enough solar power in the winter to keep things warm. So those places are too cold, too challenging for electronics in general to go explore. And so we need to avoid these dark bands. So as much as landing at a polar region on the polar cap would be sort of exciting conceptually, it's not in the cards for now. Also, what's grayed out at lower latitudes are the high altitude areas. See, there's a giant patch on the left. That's the Tharsis Bulge. It's sort of the uplifted crustal part of Mars's crust that carries most of its giant volcanoes. That's the Tharsis Bulge on the left. And then some of the highlands of Mars in the rest of the lower latitude regions are also too high in altitude for you to land. But everything else was fair game. Everything that's blue, green, yellow, orange, that is fair game to land. And just to put the site that we picked in context, the site that we picked is that little tip at the western end of this gigantic scar, this canyon, Valles Marineris, that cuts through and into the Tharsis Bulge. You can see that there is a blue and green giant scar, that's the Valles Marineris Canyon, cutting into the volcanic region.
And right up here.
Yeah. At the leftmost tip of it, there's a little spot that's almost too high in altitude, but it's yellow still. And that's Noctis Landing. Okay, and the reason why we like Noctis is sort of illustrated right here already, because it takes you to the heart of the volcanic region of Mars, where you might still have warmth, still have volcanic activity, still have options for finding extant life on Mars, life that would be alive today. So you need some warmth, you need availability of liquid water. So going to the long-term volcanic region of Mars is not a bad idea. It's sort of a good strategy. And then you are also able to access Valles Marineris, which is this gigantic 5-mile deep road cut that exists in the crust of Mars, which gives you so many options to explore Mars through time and look for fossil life in the geologic record of Mars. So this is why we love this location so much. It gives you access to the most distant geologic history of Mars, and the possibility for looking for fossil life, and options to go search for extant life in associated with the volcanoes of Mars, which might still be active. Next slide. Now, there you go. This is where Noctis Landing is. So I've been working on Noctis Landing with a few students over the past few summers. First of all, this view show, let's talk about this, what we see here first. Noctis Landing, there is that little yellow dot. It's a flat, relatively boring spot in itself.
It's good for landing, not for science. You want flat spots, I guess.
Landing, good for comms. You don't want to be on the floor of a canyon, at the base of a wall, and then you can't see the Earth most of the time. You have to have a good view to the north and the south. We are at about 7 degrees latitude south here, and the primary exploration zone would give you access to Noctis Labyrinthus on the west, the canyons to the east, Udaman's crater. I'll talk about that in a second. To the south, and then to get to the volcanoes, it's a bit of a longer drive. We'll touch on that as well. But here you are at a very interesting place that's a basin of mysterious origin, incidentally. You don't see a clear impact crater origin to this spot, and yet it's a low spot in a relative sense. So we're very intrigued by this landing site. And then with a secondary exploration zone that extends out to 200 kilometers, you can see that we could explore a lot of terrain, going deep into the canyons to the east as well. All right, next slide. So Udaman's crater is super exciting. In fact, maybe we go back to the previous slide. Yeah, thank you. A lot of people propose going to Valles Marineris squarely, you want to be where the geology is exposed. So let's land on the floor of the canyon, and then you are right there with the geology all beautifully preserved in the canyon walls right next to you. But the canyon walls are not next to you, they are above you. And that's a real problem, because if you land in a location where you see all the geology from far away, but you really can't get to it because it's on a cliff, and it would be really difficult to go explore and sample. You don't really get the full advantage of really being in a place where you have all this ancient geology exposed if you can't really sample it methodically. Sure, you can sift through the rubble at the bottom of the canyon and figure out which rock came from which layer, but good luck with that. It's going to be really tough. Okay, but the beauty here is that Udaman's crater, which you see near Noctis Landing,
right down there at the bottom, yeah.
Udaman's crater is recent enough and big enough that what it did was it basically broke up huge chunks of the walls that are exposed in Valles Marineris. And these gigantic slabs of canyon walls are now lying horizontally, but still organized layer by layer on the floor near the center and around Udaman's. Okay, so if I could go to my next slide, which is this. What you're seeing here, okay, each strip is about a couple of kilometers wide, okay? What you're seeing here are all these beautiful layers of the Valles Marineris canyon walls now laying flat on the ground, okay, one big chunk at a time, but then that's a lot more manageable. And now you can walk from one layer to another while they're resting horizontally. So the art of doing field geology is to going to places where things are not just visible but accessible. Mm-hmm. So now you can be walking around and driving from one layer to another, sampling it, knowing which layer is older than which other. You can do all your detailed fossil searching and environmental characterization because the layering is so well preserved. There. So the impact crater had the benefit of basically breaking things up and putting them flat, laying them flat for you, but at the same time not completely destroying the geologic record that was there. Okay, so that's the big advantage here of Udaman's crater. So that's about looking for ancient life on Mars. Mm-hmm. Next slide. Next slide, we look at how we might go to the volcanoes. Okay, so now it's a longer drive to get to the volcanoes themselves, but over time we will be able to do this. I did a traverse in the Arctic with a Humvee on sea ice on unprepared terrain, and we essentially were able to show that you can reasonably do 100 kilometers per day
Wow.
on terrain that is relatively trafficable if you have a good rover. So this is essentially rocky terrain with ups and downs and hummocks to cross, and 100 kilometers a day, that's sort of an average. Some days we did less, some days we did more, but
Still
100
seems like
kilometers
a
a
lot.
day is sort of, it seems like a lot, but now bear in mind, you're not doing this necessarily all in one go. You sort of
Hmm.
go by known route. So you establish a route to a point that's 100 kilometers away first, and then the next mission maybe pushes the the uh, the edge to another 200 kilometers beyond, something like that. And so over time, you build up essentially roads, known paths that you can reliably traverse. And then these volcanoes become accessible within a week or 2 weeks of driving. And
Wow.
that is super exciting because the volcanoes, once again, could still be active. Uh, we don't know. First of all, there's no sign of volcanic activity on Mars. Just to be clear, right now, we've been looking for fumaroles and hot
Hmm.
spots, and nothing so far. But some of these volcanoes are so big that they must have been active for at least 2 billion years. Some of them, and 2 billion years, that's half of Mars's history. So
Sure.
chances for them being still somehow active today are not small. It's sort of reasonable. Some of the youngest lava flows that we know of on Mars are believed to be maybe 10 million years old. Some people claim even less. Okay, so that's yesterday basically in terms of geologic history, and therefore Martian volcanoes might be dormant, but they could still be active. Some might be extinct, of course, but some might just be dormant. In any case, we are very excited by the volcanoes because, again, there are caves associated with them. Next slide. So here you are. This is one of my favorite pits on Arsia Mons, actually at the base of Arsia Mons on Mars. Actually on the sort of rise associated with Arsia Mons. This pit is called the Jeanne Pit. It's about 150 meters across. It is bottomless in the sense that we've looked at this pit. We've looked at this pit with different lighting geometries and stretched the images to death. In many pits, you can at that point see the floor of the pit,
Hmm.
but in this case, for this particular one, we can't. It's pitch black, no matter how you stretch the images. So the estimate here is that it's at least 170 meters, if I remember well, deep. Okay, so that's astounding because, well,
It's a big
it's
hole.
a huge cavity that's underneath. It's a huge cavity. Okay, and so what I have on the right here is a painting depicting, of course, a scene far in the future where astronauts are going into this cave and are finding somehow uh,
I'm just struck by
photosynthesizing
doing
life.
exactly what that person's doing on Earth without a spacesuit would be incredibly difficult and dangerous. Doing it on Earth in a spacesuit would be difficult and dangerous. Doing it on Mars in a spacesuit sounds horrifying. So kudos to that artist for imagining
Yeah.
humans are that
Well,
brave.
well, actually, I'll take credit for that. But hey, humans exploring caves like this, humans exploring caves like this is actually not that extraordinary on Earth. I mean, spelunkers do incredible things. Rappelling down into a sort of a lava tube skylight pit, even some that are tens of meters deep, are things that cavers do. I would say almost commonly. I mean, it's not even newsworthy. Is my point. It's again, we're not ready for this on Mars yet. Okay, just to be clear, but it's something to aim for down the road. And of course, before we send humans, we will scout these places out with drones, maybe.
Hmm.
And there's a helicopter that's going to Mars now with Perseverance. So the problem with these pits, of course, in caves, is that they're at high altitude. They're on the flanks of these giant volcanoes, so drones can't fly anymore. You
Right.
cannot really use
Not enough
rotorcraft at
air
that
to
point.
push against.
exactly, not enough air density. So you would have to, use maybe a gas thrusted drone, like a little drone with little rocket engines. But anyway, that's one way of doing it. Another concept is something I'm working on with JPL called Globetrotter, which is essentially a balloon, a little spacecraft surrounded by a cage, and it essentially bounces, doesn't care what it hits and where it lands. So you could just throw this off the edge. It would drop down into the cave, bounce, just like an airbag landing on Mars. And then once it comes to rest, it would study its surroundings, take pictures, flash photography, of course, and then fly back out because it has these little thrusters on it. So anyway, that's the Globetrotter concept. Bottom line here is.
Go ahead.
Yeah. No, I was just saying, Josh. The bottom line here is there's plenty to explore on Mars and lots of exciting things for humans to do. And Noctis Landing is one place that I find particularly exciting. I'm working with a student in India called Surab Shubham. He is helping us map the mineralogy on the floor of this area around Noctis Landing. We're finding some really interesting water-related minerals and deposits, which means that this is a place where we could probably extract water easily from some of the minerals that are there. With another student, I've worked on extracting water from the atmosphere of Mars in that location. People have now ruled out extracting water from just compressing the Martian atmosphere because the compression ratios are too high and the water content in the Martian atmosphere is too low. But that's on average Martian atmospheric content. If you look at this particular location, one of the first slides that Mary showed here earlier today shows you fog filling these canyon floors frequently. And when you have fog, the water concentration in the atmosphere can be about an order of magnitude higher than it is elsewhere on average on Mars. So
before we flew away, though, I wanted to show folks one last really cool detail we can see. If I get close enough and there's a fine balance, you can see some features on some of these, which is like sand dune variation. Now, I don't know that that's actual sand dune accumulating on the surface, but anytime you see a detail like that, it's beautiful. And if folks want to check this out and visit some of the places that Pascal has shown us, download OpenSpace, try it out. You can go from where you see sand dunes to where you see the entirety of Valles Marineris. And that kind of ability to fly around Mars is something really special, and with some context becomes a really amazing adventure for you to take yourself on. But we have some other places we want to hit before our program winds down. So I was going to introduce the outer part of our solar system and head a bit farther out.
Yeah.
We're heading to Titan next, I believe.
That's right. Titan. I think it's, now that Mars is sort of squarely on the map of where we plan to go, what could lie beyond. And I think beyond, I don't think Venus will never be a good place to send people.
Pretty tough for humans.
Unless you're into sort of cities in the cloud type of thing. Titan is, I think, really an exciting place, and let's go see why.
Let me see if I can get Titan to show up.
So Titan is one of the largest moons in the solar system, and Saturn's largest moon. Okay, Titan. But I almost think of Titan as an exoplanet in the sense that, it's really far away, but it's sort of like a Earth-relevant world. It has a solid surface. It has a thick atmosphere. In fact, it's one of the only moons that has a thick atmosphere, and it's astoundingly thick because it's thicker than the Earth's atmosphere. Titan has a surface atmospheric pressure of 1.45 atmosphere, 1.5 atmosphere. So it's 1.5 times denser. At the surface of the atmosphere has a pressure that's 1.5 times what it is at the surface of the Earth. So, and the atmosphere is made of mostly nitrogen. Okay, 95% of it is 98% of it is nitrogen on Titan, 95% of it is nitrogen, and then you have methane as a secondary component, which of course is a toxic gas for us, but it's an organic gas. So Titan, of course, is this incredible world where we hope to be able to study prebiotic chemistry, the early phases of organic chemistry that led to the origins of life on Earth. And of course, NASA is planning to send this incredible Dragonfly drone mission to Titan. And indeed, it's a great idea to fly in such a thick atmosphere. And the gravity is low as well, so the flying is very efficient on Titan. Gravity on Titan is even lower than on the moon. The moon's gravity is 17% of what it is on the Earth. Titan's gravity is 14% of what it is on the Earth. But what is incredible with this thick atmospheric pressure is that opens the door for humans to possibly explore Titan one day. Okay. Because now what you need on Titan is to just protect yourself from the methane, I guess, in the atmosphere, because that's really a lot. And you need to still have an oxygen supply, but you don't need a pressure suit anymore. You do not need a pressure suit. Let me repeat that. You do not need a pressure suit. You don't have to be sort of ensconced in this rigid, pressurized bladder that a spacesuit normally is. A Titan suit just has to keep you warm and insulated from the toxic gases that are outside.
Warm sounds really important.
You certainly have to be kept warm. Yeah, exactly. Because the temperature at the surface of Titan is minus 180 degrees C, so that's 94 Kelvin.
Not
I
warm.
have no idea what that is in Fahrenheit.
We say about negative 300 Fahrenheit.
Okay, all right, there you go. So you need more than a parka. You need some really good insulating equipment. A head mask to breathe oxygen. And I'm also working with a student this summer. In fact, it's a high school student who's helping us with the design of a spacesuit for Titan. Okay, so we haven't published that yet, but once it's ready, we will get that out. The student is Joe Nadiju. He lives in the Bay Area. And anyway, I think he'll forgive me for mentioning his name. He's still in high school.
We had, I think, a really cool shot of Titan's surface, because what we're showing folks is actually a map of infrared mapping done from above. But yeah, can you tell us a little bit about what we're seeing in this picture?
Yeah, so this is an actual image of Titan during descent of the Huygens probe as it was about to land. It took this aerial view of Titan as it was sinking through the haze, the organic haze of Titan's surface. So this is from the European Space Agency. It's an image processed by somebody who has my last name. Pascal is his last name, actually, but no relation. Anyway, it's a beautiful scene that shows you what it's like to sort of descend to the surface of Titan. And next picture is. Yeah, go ahead, Josh.
The next picture. This would be more like the colors our eyes would see should we be there, not so much gray and black our imagery.
That's correct. But once you get underneath this haze, it gets quite a bit darker, okay? Because the surface, you can tell, is dark. And so this bright scattering that you see at the surface is something that you would see at high altitude. But once you're on the surface of Titan, the skies become quite a bit darker. Next slide.
Oh, that's beautiful. Seeing Saturn kind of on the limb.
So that's right. So that's actually a painting I did of what Saturn might look like from the surface of Titan, where there are actually lakes of methane, liquid methane, and ethane. So it's a carcinogenic goop that is at the surface, but it's still very beautiful. You can sort of see the carcinogens. And actually, it's not even clear if the atmosphere of Titan ever breaks up enough for you to see the disk of Saturn. But painting Saturn from Titan is such an iconic sort of perspective in the history of space art that I had to try my hand at it. But by just allowing Saturn to be seen fleetingly, in a brief break in the haze, in the toxic haze of Titan's surface. Okay, but so here you can tell from the picture, since the rings of Saturn are vertical almost, that you are near the equator of Titan. Okay. So Titan always shows the same face to Saturn. It's synchronous rotation, just like our moon is. And so here we are, somewhere on the leading hemisphere of Titan. Next slide.
That's a great one. This must be from the lander.
Yeah, this is actually from the pod, the capsule that landed Huygens, the Huygens probe from the European Space Agency that was carried to Saturn by NASA's Cassini orbiter. So the Huygens probe landed, and with this is of course an enhanced image, but it landed on this boulder field. And what's amazing to realize is that these boulders are made of water ice, most of them at least. And so you're looking at a world that is so cold that rock is literally the main rock that is at the surface of this world. And so there you go. Boulders of ice coated with organic goop.
So here we are looking from Titan
so
towards Saturn.
I think we need to wrap up, right?
We're getting pretty close, but I think we got time for our one last view of kind of the macro scale.
Yeah, so why do we bother to do all this? And I think of course it's because, I mean, for me personally, it's the science, it's the search for life in any form. But what's important to realize is that what we are searching for is an example of alien life. We realize that just finding life on Mars is not necessarily the everything. What you really care about in this whole process is to try to find an example, a first example of an alien life form. So, even if we were to discover life, a sign of life on Mars today in a fossil form, I'd be happy and excited, but it wouldn't tell us really what it is, because it could be just Earth life exported to Mars. Or we ourselves, in some more extreme scenario, could be Mars life exported to the Earth, a long time ago, and then we took off from there. I mean, those planets are not isolated. Mars has meteorites that have landed there that have come from Earth. Vice versa, we have meteorites that have come from Mars. Planets are not isolated systems. Life could have been transferred from one planet to another. And so finding life per se on Mars won't tell us necessarily a lot about how universal life as a process is in the universe. And, even if we found this weird fossil on Mars, we wouldn't be able to tell for sure that it's alien life. Which is why I think it's so important that we focus on trying to find living life on Mars, extant life. Because if you find extant life, you can then do genetics on it. And then you can determine genetically whether it has anything to do with Earth life or not. Okay. And if it was to be found to be genetically really different from Earth life, you can only do genetics on something that's still alive or has been dead for not a long time. It's only if you can establish that it's genetically radically different from Earth life, which has a lot of commonalities genetically, that you could conclude that it's really alien life. Okay, so an entirely different approach, of course, to searching for alien life is to try to find signs of alien intelligence out there. And we can squabble about what we mean by intelligence, and whether or not we ourselves are intelligent or not. That's all fun to argue. In fact, Carl Sagan used to say that the surest sign that there is intelligence out there is that they haven't tried to contact us. But anyway, the thing about intelligence is that we have to realize how extraordinary it was as an event on the Earth. Okay, from the standpoint of intelligence reaching the point where it can come up with Maxwell's equations, build radio telescopes, and become a technologically communicating civilization. All right. So never before us humans did that ever happen, or it was even close to happen in the history of the Earth, as far as we can tell, for 4.5 billion years. Life on Earth appeared very early.
Mm-hmm.
Like as soon as we had liquid water stable at the surface of the Earth, life started to emerge in those waters. We have fossils that date back pretty much to the early youth of the Earth. Okay, but intelligent life took its sweet time, and in fact wasn't even necessary. Didn't even happen as a necessity, it seems, but more as a happenstance adaptation. So here's the thing: we are, of course, wanting to have have an open mind on this. We're looking for extraterrestrial intelligence in space. And I'm going to give a talk actually next month as part of Wonderfest and the Bay Area Science Festival about this in more detail. But I've been basically trying to make the case that if you actually look at the numbers, and there's an equation that helps us organize these numbers, which is called the Drake equation. The Drake equation gives you the number n, capital N, of advanced civilizations in the galaxy right now, as a multiplication of 7 terms. It's the rate of star formation in our galaxy times the fraction of those stars that have planets, times the fraction of those planets that have an environment suitable for life in that planetary system, times the fraction of planets on which life actually emerges, times the fraction of those planets where life becomes intelligent, times the fraction of those planets where intelligent life becomes capable of technological communication, times the average longevity of a civilization in our galaxy. So if you knew the exact value of each term, you would have the number n of advanced civilizations in our galaxy. Let me say immediately that we don't know the exact number of each one of these things, which is sort of the problem and at the same time the opportunity. But if you plug in the numbers that we know from the Earth, bearing in mind that it's a unique example, it's a unique data point, it has, therefore, it's very flawed as a data set.
Sure.
Because it's a single data point data set. But if you plug in the numbers that we learn from the Earth, the real showstopper is how long it took intelligence to emerge on Earth. Okay, life itself appeared quickly. Intelligent life took 4.5 billion years. In fact, it's you can come up with a way to estimate what that means in terms of the probability of intelligence emerging, but basically it's going to bring down the number n dramatically to the point where n turns out to be roughly 1, give or take. The give or take is very important because there are huge error bars. So we should still search for intelligent life in our galaxy. We should still be listening. But what this tells us is that our expectations should be low, because the number n of advanced civilizations in our galaxy, if the Earth is representative at all of all the processes and steps that need to be taken for intelligence to emerge and a communicating society to appear, the number of civilizations in our galaxy is very low, of order 1. So we are it, or there might be another one out there. And if it's sort of randomly placed, we have a galaxy that's about 100,000 light years across. The other one might be, I don't know, on average 50,000 light years away. That's a great distance away. For all intents and purposes, we'd be essentially alone. So I'll flesh all this out in my talk next month. But we basically might be living in a...
We had a couple questions pop up. I was just going to say, a moment to field some.
Yeah, why don't we do that?
So we had a question coming in from Corey. Can you tell us more about how you got into science and your fields of study today?
Yeah, I've always been interested in science and engineering. I credit television for that. Science fiction television, Star Trek, Lost in Space, Thunderbirds, TV series that got me interested in science and technology. But then the moon landing was a big thing that I was just barely old enough to witness and be in awe of. And then I read Carl Sagan's Cosmic Connection when I was a young teenager, an early teenager. And that book really made me decide to become a planetary scientist. This was the book he wrote before he became world famous with Cosmos. It's called The Cosmic Connection, and I would recommend that reading to anybody. Anyway, that's the book that made me want to become, a planetary scientist. And then from then on, I studied geology first, studied the Earth. And after that, I actually had to spend a year in Antarctica, so I went for a year. And then I went to grad school again to study astronomy. And I was actually lucky to be Joe Vaverka's last graduate student at Cornell and Carl Sagan's last TA at Cornell. So I studied planetary science, and then and then I started working after that. So in terms of what I study mostly Mars, but also the moon as a stepping stone to Mars. And I'm also interested in where we go from there, which is, I think, Titan beyond that. So lately I've started working on Titan a little bit as well with different students.
Some pretty fascinating stuff. Another question, I hear lots of talk about Mars, Europa, for places where there could be life, but not the moon. Is it possible that microbial life could be found in those sheltered caves? Like, is the moon still a place we are looking for life?
Well, we're not expecting to find life on the moon. Well, first of all, there is life on the moon because we landed stuff on the moon that wasn't sterilized, and we've crashed things that apparently carried tardigrades. So there is life on the moon. I have news for everybody. There is life on the moon. And when the Apollo 12 astronauts brought back a camera, the Surveyor 3 lander, there were bugs from the Earth that were still alive. So we think that there's at least Earth life somehow in stasis on the moon. They're not happy. They're missing liquid water really badly. So they're not, metabolizing or anything, but there could be Earth life already there on the moon that was brought in by us. Now, as far as alien life thriving on the moon, we don't anticipate that's a possibility, because you need more than just ice or water. You need liquid water. All Earth life needs liquid water, and I don't think it's a Earth life centric argument. Liquid water is chemically, a very important thing. It's a neutral solution that allows chemical exchanges to take place in a neutral environment. And so if you don't have an environment that allows you to have liquid water, then you're not in very good shape. But so there's no expectation to find any form of alien biome on the moon, whether you are in the permanently shadowed regions or not. Okay. But we still have to protect these places, and there you have it.
I think we have time for one more question. Let's see. We had a cool one come up about spacesuits. So, are you still involved in testing spacesuits? You were mentioned in a conversation with Andy Weir of Martian fame. You mentioned wearing them and see how well they hold up here on planet Earth.
No, we are involved in testing space. In fact, we could not go to the Arctic this summer, where we go every summer to do some spacesuit testing, among other things, because of COVID. But we have a plan B, so we're going to deploy to a closer location that I'm not prepared to disclose yet. We have a deployment in the works for October, and where we will be testing a new spacesuit, and all of this in preparation for the moon. So yes, spacesuits are not just clothing, right? They are wearable spacecraft, and in fact, it's sort of the minimalist approach. To me, the spacesuit is sort of the greatest tool that you can give a geologist to allow her or him to, explore the surface of the moon or Mars. It's a real gift. It's a research tool, in addition to being a wearable spacecraft and
it's probably pretty good COVID protection if you never take it off, but that doesn't seem like an efficient use.
Yes.
You got a
unless it's
shout
inside.
Out from Saurabh saying thanks for mentioning, and a bunch of other accolades
from India. Yeah. Saurabh is a very bright student at Kharagpur, India. Hi, Saurabh.
We are elated to have you watching. But thank you, Pascal, Dr. Lee, for giving us this insight into all the cool things that are happening with human exploration beyond Earth. Any parting words for our audience?
No, it's an exciting place out there. We should go explore. And
we may have had your audio drop out momentarily, but we'll see if you come back. But I would like to thank all of you for joining us here for our broadcast. It has been a joy bringing you some of the insight on where human beings might be ending up in the not too distant future. From myself, from Dr. Lee, from Morrison Planetarium, thank you all for joining us. And thank you, Dr. Lee. It is a joy. Okay. Have a wonderful rest of your day, and we hope to see you again soon. Goodbye.